Today we'll be talking about rotational motion and angular displacement. So what is rotational motion? Well, basically you have an object that spins. It rotates around some central axis. Looking at this figure skater, the simplest kind of rotation, we consider the object rigid, and all parts A, B, and C rotate around some central axis. And if we consider the object rigid, then points A, B, and C all complete the same amount of revolutions in the same amount of time. The angle through which they rotate is called angular displacement. Okay, so if you take the idea of this line here, and the whole disk spins, started here, and it went through this much rotation, that would be defined as the angular displacement. It would take the final displacement, like right here, measured from a reference line, minus the initial displacement, measured from a reference line. That would be the change in displacement. And it's very similar to the idea of linear displacement. Okay, let's actually define angular displacement. When a rigid body rotates about a fixed axis, the angular displacement is the angle swept out by the line passing through any point on the body and intersecting the axis of rotation perpendicularly. All right, let's look at that a little closer. We'll pick any 2 points on the disk, and I represent them by the 2 stars. The angular displacement for both of them will be the same, even though the outside point travels more distance. So the further you get from the axis of rotation, you're going to cover more linear distance basically, but you'll cover the same angular displacement as something closer to the axis of rotation. Like this only had to go through this much distance, this one had to go through that much distance, but they went through the same angular displacement. Now we have to think about how we're going to label a direction. Like with linear, we think of north, south, east, west, and defining one of those directions as being positive and another direction as being negative. So we have to do the same thing here with angular displacement. And by convention, we call counterclockwise positive and clockwise negative. Now once again, this is completely arbitrary, but the normal convention is counterclockwise is positive and clockwise is negative. So what are the SI units? They're what's called radians. So what is a radian? A radian is an angle whose arc length is equal to its radius. All right, let's look at that a little closer in the next slide. Okay, so we'd spin the disk measured from some reference line. So the arc length, S, is equal to the radius, R. Now what's interesting about this, no matter how big the object is, if it's a larger object, the arc length will be larger, but the radius will be larger. So it doesn't matter how big the object is, it just matters how far you spun it out or displaced it angularly. So there we go. A radian is when the arc length is equal to the radius. This arc length is equal to the radius. And notice there's no units, because if S is measured in meters and R is measured in meters, the two would cancel out. If it's measured in centimeters or inches and inches, it still cancels out. So let's look at one revolution. That means you start at some reference line, you went all the way around, and then back again. So if that's true, you covered the arc length would be equal to circumference, and the radius would still be the radius. So what is the circumference of a circle? 2 pi r. The r's cancel out. So for one complete rotation, you've gone to 2 pi radians. And let's equate that to degrees. So therefore 2 pi radians is equal to 360 degrees, because there's 360 degrees in a circle, and we've gone through one circle. And also therefore pi radians is the same thing as 180 degrees. Okay, we have 2 satellites, and the distance from the center of the Earth is 4.23 times 10 to the 7th meters. That would be r. The angle between the two is 2 degrees. And what we're looking for is what would this arc length be when the satellites are that far away from the center of the Earth. Okay. Well, we know that a radian is equal to, is defined as being the arc length divided by the radius. So we can use this equation to figure out what s is, because we know the radians and we know the radius. Right? So we can take s, arc length, is equal to the displacement times the radius. But this must be in radians. So we need to take 2 degrees and change it to radians. Alright, so we have 2 degrees. And how do we get that into radians? Well, we use the expression that we derived before, that 360 degrees is the same thing as 2 pi radians. So degrees on top cancel degrees on bottoms. You're left in radians. After you multiply it through, you end up with 0.0349 radians. Okay, so now we use the equation for arc length, and we can now solve for the arc length s, and the arc length is 1.48 times 10 to the 6 meters, which is the same thing as 920 miles.